Yeah, we're going to organize the elements from the lab by metals, metalloids, non-metals. So first off, look at your data table. What's the first element on the data table? Aluminum. So if you see aluminum here, that's to the left of your metalloids, which makes it a what? Metal. So aluminum's a metal. What's the next element on the data table? Carbon is to the right of the metalloids. So that's a non-metal. So carbon's a non-metal. And then after that, what's the next element? Copper. So you find copper right here. It's to the left, so that's going to be a metal. That's kind of obvious. After copper, we have iodine. So there's iodine right there to the right of the metalloids, making it a non-metal. And then we have magnesium. So there's magnesium. It's obviously to the left of the metalloids, making it a metal. And then after magnesium, silicon. Look at that. We have silicon. It's the most famous metalloid. After silicon, what do we have? Sulfur to the right, making it a non-metal. And then I think the last one is zinc, right?
Yes, sir.
Zinc metal. Okay. Isn't that all it asked for?
Yep.
Okay. On number 2, we're drawing the Lewis structures for the alkaline earth metals. And then we want to draw a diagram that illustrates how they become ions. Say that one more time. Well, I want you to draw a picture of it. And don't worry, I'm going to draw the picture with you. So draw Lewis structures for alkaline earth metals, then draw a diagram to illustrate how these become ions. So your alkaline earth metals, you have beryllium. That's 2 valence electrons, right? So those 2 valence electrons are I did that with you before just so that you can get used to the idea that they're separated, but when we draw them out, they're actually going to be paired up because that's the s orbital. So that was just a way for you to get used to the idea of electrons not liking each other and to stay they stay far away. So beryllium has 2 valence electrons. These electrons are pulled away from beryllium by a strongly electronegative atom. So those electrons go away. When they go away, beryllium becomes +2 or 2 positive. When that happens, it's stable. So beryllium is happy because he's stable with 8 valence electrons. Okay, so that's kind of the long version. With the rest, we can kind of get to the point, right? Magnesium, 2 valence electrons, they go away, and then magnesium has a 2+ charge. Let's do 3. Then you have calcium with 2 valence electrons. They go away. Calcium has a 2+ charge. We'll just, we want to go with a little repetition here to get the point across. The more you do it, the easier it gets. You need to understand that those electrons are taken away because another atom wants the electrons more. It's more electronegative, and when that happens, that's when you get that 2+ charge. So the electrons are donated, and when they're donated, that's when you get the 2+ charge. Okay, number 3, very similar. We want to draw the Lewis structures for halogens and then draw a diagram that illustrates how these elements become ions. So your halogens, what group are the halogens?
7.
Yep, so halogens are going to be in 7A, or the way it's written is 7A. First, you have fluorine. If they're in group 7A, how many valence electrons do they have?
7.
7 valence electrons. So first you start off with a neutral fluorine atom. Then that neutral atom, it needs 8 valence electrons. It only has 7. Is it easier to gain 1 or donate 7? It's easier to gain 1. So you have a valence electron that comes in from another atom, and fluorine is highly electronegative, so it pulls the electron away from another atom, and when it does that, that's right, it has 8 valence electrons now, giving it a negative charge. So now that fluorine has a full stable electron configuration with 8 valence electrons, it's no longer trying to take electrons from other atoms. It's stable but with a charge. Same thing happens with all the other halogens. Chlorine has 7 valence electrons. An electron from somewhere else comes in, making it full with 8 valence electrons and a negative charge. Then we'll stop at bromine, because I think you guys get the idea. Okay. Number 4, explain how chemical and physical properties of elements relate to their location on the periodic table. So just take a minute to write this question down, and then we'll go over it together. So there are a lot of different ways that we can actually look at the location. If we're going to look at different elements in their location, there's a lot of ways we can describe that location. We could say that it's in group 1, we could say group 2, group 8, group 7. But when you start doing that, then it gets really specific. So we're going to kind of be vague on this, and we're just going to talk about the generic position of different atoms. We're going to break it down simply into metals, metalloids, and nonmetals. That's how we're going to do this. So you have your periodic table. That's arranged by metals, metalloids, and then nonmetals. Your metals, what are some physical properties of metals? So they're shiny. What are some other properties? Malleable. Malleable, yeah. What are some properties of nonmetals? Mostly solid. Yeah, they're mostly solid. I guess with chemistry you have a lot of exceptions. So nonmetals are brittle. So brittle, dull, non-conductive, assuming they're in the solid state, because you have nitrogen, oxygen, fluorine, chlorine. Those are all gases at room temperature. But if they're solids, these are pretty good properties. What about metalloids? What are some properties of metalloids?
Some of them are shiny. They have emissions both. Some of them are shiny.
Yep, so they have properties of metals and nonmetals. So your metalloids, kind of both. It depends on what it's bonded to. So what about chemical properties of metals? What are some chemical properties?
They easily corrode.
They easily corrode, okay. Here's one that you guys aren't familiar with. We know that they're going to, do they lose electrons, gain electrons, or share electrons? They lose. So your metals lose electrons. So when they do that, they end up forming ionic compounds.
Thank you.
Yeah, they form ionic compounds with nonmetals, with nonmetal ions. So they corrode, they form ionic compounds with nonmetal ions, and that's basically what corrosion is. If you think of rust, it's kind of the same thing. It's a metal oxide. And then the reason that this happens is because they lose valence electrons. So they lose valence electrons. Your nonmetals, they form ionic compounds with metal ions. They form ionic compounds with metal ions. And the reason this happens is because they accept valence electrons. So they accept valence electrons. And then your metalloids, they lose, gain, share. Oh yeah, and by the way, nonmetals also share valence electrons. So your nonmetals accept valence electrons, share, accept or gain, I guess you could say, valence electrons. Your metalloids can either lose, gain, or share, and then your metals lose valence electrons. So when you think about the breakdown of the periodic table, you have your metalloids. Anything to the left of the metalloids, they're metals. What do they all have in common? They're all shiny. What else do they have in common? All their physical properties. What else do they have in common as far as valence electrons are concerned? They lose electrons. So since these are all to the left of the metalloids, they all lose valence electrons. That determines their properties chemically. Then on the right side, you have the nonmetals. They all gain or share electrons, so they have similar properties. And then, of course, your metalloids, they have properties of both. So I want to give you all 1 minute, now that we have this kind of organized and you can see all this, the differences between these types of elements. I want you to take 1 minute and answer the question.